the use of colors in scientific visualization. We'll go into how color is defined, how we perceive color, and what color maps are useful. So how do we define a color? There are actually 3 independent values necessary. That was shown by Mansell already very early. I think it's 1905 and not 1995. So I think there's a typo in the work rational way to define color. You can see he defined the color on 3 values. They're called value, hue, and chroma. So chroma depends how colorful, so to say, the color is. The hue determines the actual color, and the value determines the so-called lightness. And this is not the only way to define color. There are several ways, especially now on the computer. You can define colors, for example, in the RGB color space. So there's basically a color cube that is spanned by 3 axes. One is blue, one is red, and one is green. And then depending how these colors are mixed, you get the result. Another option is the HSL or HSV system, where you define the colors by hue, saturation, lightness, or value. So this is closest to the definition by Mansell. Again, here you see how the color space is spanned by these 3 values. You can also use the XYZ color system, where you sort the colors depending on the wavelength, and then you basically distribute how much of red, green, or blue is in this color. And a last method is the so-called lab color space, which defines a lightness value, an A value, and a B value, where the A value maps between red and green, and the B value maps between yellow and blue, and thereby defines the color. So these are the most common color spaces that are used to define a color. So the next topic is, how do we perceive a color? So the first thing to notice is that there's actually no natural ordering between different colors. So the sorting by wavelength basically is an arbitrary choice. You could also have chosen to sort blue after yellow or green after red. This is the wavelength sorting is basically arbitrary, and you can never say what these values correspond numerically to. The other thing in perception of color is that perceptual changes in color are not uniform. And this is simply explained by this example here. Which peaks are higher? Are the red or red-yellow peaks, or the blue peaks higher? You can't really tell. If you look at the same color in a black and white diagram, you see they're actually the same height, but in my perception, the red peaks are higher than the blue peaks. The perception of luminance, so how bright the color looks like, are actually depending on the surrounding area. When you look at these 2 bars in the center here, the gray bar and the red bar, they don't look to have the same color or the same luminance, so to say, but they actually have. So if you blend out the surroundings, you see that this is exactly the same color, but it looks much lighter when the background is dark. Another problem with color perception is that often colors interfere with the shading of 3D surfaces that is usually applied to reflect the lighting of a 3D structure. So this interferes. And what you also should think about with color perception is that some people might have deficiencies in vision. For example, they can't distinguish between red and green. So make sure your color representations are also useful for everyone. So what are color maps now? That's what we usually use as a tool. A color map simply maps numerical values to colors, because we need to interpret numerical values from the colors that we use for the visualization. And therefore, this color map should be perceptually uniform. That means we can really map our perception to a numeric value of the data. And the choice of color map clearly determines which features are visible in the data. So they should be chosen with care, such that we actually use them to visualize what needs to be shown. So how can we choose color maps? First, we need to know what types of color maps we have. We have qualitative color maps, so they simply are different colors, not sorted in any way. Then we have sequential color maps, where we usually have one color, and we can clearly see the sequence in the color. We order them naturally in the right way, and we see how the ordering is. And there's a diverging color map. So this is basically two sequential color maps put together, and we have a distinctive value in between. So when do we use a qualitative color map? This is a typical choice where there's no order in the data possible. For example, element type. You can't really say, it doesn't really make sense to order them numerically by the number of nodes, since there are different classes of elements. Then we have sequential color maps for data where we have a metric relation between the values, for example, equivalent stresses or displacement magnitude. So there it is clear we have a metric in the data. And the same holds for diverging color maps. However, they should be used especially if there's a significant sign or critical value. For example, stress components, they can be positive or negative, and it might matter if they are positive or negative. So you want to make sure that the zero value is actually in the white, so to say, where the two sequences match. Similarly, you could shift this value of the color change to, for example, a critical stress level that should not be exceeded. So if you're coming close to this, or if you have exceeded a critical value, it gets light red, and if you have exceeded it very far, it gets dark red. So use this color map to show what is important in the data. And last remark to colors, avoid a rainbow color map. It's still the default in many visualization programs, but for the typical thing you want to visualize, it is not suitable.